Now, section 11.7 is a summary section for series. This is a good section. I get my dog to shut up. This is a good section for review, for practice in dealing with the convergence and divergence of series. I would recommend looking at some of the homework in this section because the problems are in no particular order. I mean, that's what you're going to see on the test. I'll give you some series and say, hey, determine whether or not the series is convergent or not. Shut up, you mutt. And so, really, all this is just a kind of a step by step things to recognize, or the things that you look for in applying those different tests that we've been talking about, right? So, and we keep saying with this, and that makes it difficult. You take each of the tests in isolation, and they're pretty straightforward. I mean, we talked about different types of series like P series and geometric series and how we recognize whether they're convergent or not. How do I use a comparison test? How do I use ratio tests that we talked about in the last section? Alternating series tests. Each test on its own is a pretty straightforward deal, but the big problem is you have to recognize when to use which one, right? So very, like we said, very similar to what we had talked about with integration. You have to recognize the process, but each process in itself is pretty straightforward. It's a pretty standard operation. All right, so these are recommendations. So what do I look for? How do I, if I'm going to make a determination as far as whether a series is convergent or divergent, what do I look for? What are the series, or what are the tests that I have at my disposal? All right, so first thing, I'll scratch out an old page number, so just disregard that. But there is a summary, a summary similar to this in the section, a little more detailed than what I have here. This kind of hits the main parts of it. So first, and really 1 and 2, looking for those two series or types of series that we recognize. P series and geometric series, right? We know that a P series is convergent if P is greater than 1. We know that it's divergent if P is less than or equal to 1. So if I recognize a series of the form of a P series, I can determine convergence and divergence straight away. I don't have to do any fancy test. Number 2, similarly for a geometric series, we know that geometric series are convergent if the absolute value of R is less than 1, divergent if the absolute value of R is greater than or equal to 1. So again, if I recognize that my series is a geometric series, then there's really no work to be done there. And I can determine convergence or divergence. Now, we did also come up with a way to calculate the sum of a geometric series, right? So if we did have a convergent geometric series, that was the one type that we were able to actually calculate the sum. That was that A over 1 minus R little formula. Right? But for convergence and divergence, that's primarily what we're interested in, that determination. Number 3, if the series is of a form that is similar to a P series or a geometric series, right? So it's like, okay, I look at this series, it's like, okay, it's not exactly a P series or a geometric series, but it's very similar. It fits the basic format. That's where your comparison tests typically come into play, whether it's the direct comparison test or the limit comparison test, whichever one is applicable. All right, so especially when you see rational functions or algebraic functions, roots of polynomials, as again, primarily you're looking at a numerator, denominator that are polynomial in form, right? Then the series should be compared to some type of P series, right? But again, you're looking at polynomials into powers, right, into constants. Now, your P series should be chosen by, if you compare the degrees of the numerator and denominator. So say, for example, I have in the numerator, my highest degree is n. In the denominator, I have n squared. So I would compare that to 1 over n. And if you take n over n squared and simplify, you get 1 over n. What if I had n in the numerator and n cubed in the denominator? Right? I would maybe compare that to 1 over n squared. N over n cubed, simplified to 1 over n squared. So that's what I mean by you kind of compare the degrees of the numerator and denominator, simplify the highest degrees of each, and that may give you a suggestion. And again, none of this is 100%. And we always say that's the problem with this. There's no guarantee that this is absolutely going to work, but it at least gives me a pretty good place to start. Right? And then I could maybe try a comparison test with a similar P series. Right? And again, you have the two different comparison tests, right? Direct comparison or limit comparison. Now, comparison tests only apply to series with positive terms. And so we didn't make a big deal out of this, but even when we did the we did the absolute convergence, right? We did one where we used a comparison test, but we had to compare it to the absolute values of the terms of our series, because comparison tests are only going to be useful, only going to work if our series contain strictly positive terms. Very difficult to compare if you have alternating or different signs of your terms. Now, if the sum of a sub n has some negative terms, some positive terms, right, then we can maybe apply the comparison test with our absolute convergence, right? We did an example of that back in 11.6. So using absolute convergence, possibly with comparison test, that still applies. Even though typically, most of the time, absolute convergence is done with ratio test, don't forget you can still do it with comparison. Right? It's all about the absolute value of my series and whether or not that converges or diverges, and then what it tells me about the series itself. Number 4, we always say with this, don't overlook the most obvious, right? That test for divergence. If you look at the limit as n approaches infinity of a sub n, we said in order for the series to converge, that limit has to be 0. And so if that limit is not 0, then automatically it's a divergent series, and there's nothing else I need to do. But it's kind of a basic test that it gets overlooked because we get caught up in all these more complex or intricate tests like ratio tests and comparison tests. Don't forget about the basic test for divergence. If the limit is n approaching infinity of a sub n is not equal to 0, the series is divergent. Number 5, alternating series test. Alternating series test is pretty recognizing when to use it. When you have that negative 1 to a power times some expression, right? Now you see that a lot of times too with ratio tests or using it for absolute convergence, but alternating series test will apply. We said if two things happen. First of all, if the limit as n approaches infinity of the b sub n, of the positive part, is 0, because we know that has to happen for convergence. And then if we have those absolute values that are decreasing, right? We said so you compare b sub n plus 1 to b sub n. And if those are getting smaller, the terms, the absolute values are getting smaller, and the limit is n approaching infinity of b sub n equals 0, then you have a convergent series. Now remember too, alternating series test, that's all it can be used for. It can be used to determine if a series is convergent, if it meets those two requirements, okay? Otherwise, if it fails this requirement, right, well, that's this. That's test for divergence. Right? So we said if it fails the limit test first, that's test for divergence. That has nothing to do with alternating series test. Okay? So be careful with alternating series as far as what it actually tells you. The only thing you can make a determination of with alternating series test is that a series is convergent. You can never use alternating series test to determine or say that a series is divergent. Okay? Because all it says is if you meet these two requirements, you have a convergent series, and that's it. Okay? So be careful there. Don't read more into it than what it says. 6, ratio test, right? So we said that's our absolute convergence, right? Testing for absolute convergence and then possibly convergence from there. And I tell you that if you're looking at a series that involves factorials or, combinations of different types of expressions, like products of different things, then using ratio tests to determine absolute convergence may be a route that you can take. Let's see, constants raised to the nth power, we say that kind of thing. So combinations of like exponential and factorials and polynomials, right? We have a combination of different things. 7, I said root test, not a major player, but if you do have a series, a sub n of the form, some expression or some function of n raised to the nth power, right, then the root test may be used. And you take the nth root of the absolute value of the series and make the appropriate observation, whether that is less than or greater than 1, equal to 1, and conclusive. right, for ratio test and root test. Lastly, 8, the integral test. We said that's one that's pretty limited in terms of how or when you can use it. Don't overuse integral test. We said that if a sub n is equal to a function of n, where I'm comparing it to f of x, right, the more general function, and I'm looking at the integral from 1 to infinity of f of x dx. Now, of course, if that integral is easily evaluated, certainly I don't want to try to use integral test if I end up with an integral that's difficult or impossible to find the antiderivative of, right? Because then, of course, it's not going to do me any good. So I do at least want to, try to use it with a function that I can actually integrate. Then our integral test can be used provided that you meet those requirements. We had 3 requirements for integral test. Function has to be continuous, and we're talking about the f of x here. That function has to be continuous, has to be positive, and has to be decreasing over whatever the integral is that you're integrating, right? 1 to infinity, or sometimes we had to adjust that lower limit depending upon the domain of the function, right? But those were 3 requirements. It had to be continuous, has to be positive, has to be decreasing over the interval, 1 to infinity, or whatever the interval may be. Then we can make the comparison that if the integral is convergent, then the series is convergent. If the integral is divergent, then the series is divergent. And then we also made the statement as well that if the series is convergent, the sum of the series is not the value of the integral, right? That's where we kept talking about the convergent series lies below the convergent integral, or the divergent series lies above the divergent integral, that kind of thing. So if you do have a convergent series, provided you meet the requirements to use this thing, I can't go through that enough because that's where I see misapplication of integral test. It has to meet the requirements. Then the convergent integral means you have a convergent series, but the sum of the series is not the value of the integral. It's less than that. We know it's going to be smaller than that. All right, that's section 11.7. Again, it's just kind of recommendations, suggestions. I would strongly recommend that you look at some problems in that section to practice, because that'll give you a good idea of what you're going to see on your test. And that's 11.7.